they're a parts distributor, yeah, but they still have conveyors. But work on lighting, but it's not a manufacturing processing plant. Okay, what are we doing? Last day of class is Monday, so a week from today is going to be our final. So today we're going to go over chapters 19 and 20, do some examples, and then Thursday will be all about preparing for the final, which is Tuesday, the 7th, a week from today. Yes. Yes. Here's the thing. There's no way I can force that stuff on you before we take the final. So I would recommend that you go through that or try to get that homework done. But yeah, I made all 4 of those due 2 days after we take the final, just to give you some extra time if you. And here's the other thing. So here they are on the 9th. All 4, 21, 22, 23, and 24. But I also gave you unlimited attempts. Do you understand what I'm saying? I'm giving you permission to just, I don't want to say the word. It starts with a C and rhymes with Schmeat, but it's kind of, I don't really care. Like, it's, yeah. We're getting through the bulk of the hard theory stuff and the reactants, which is yeah. So that's the upcoming schedule. Everybody understand? Just to backtrack a little bit, are you guys going to email me? Let me know if you're interested in that apprenticeship. What? Okay. Why don't we just do this now? My mom. What you said? All right, raise your hand if you are interested. This is not a commitment to interview or apply or anything. Interested and then Dylan. Let's say your name. You put your hand down. Zach, Alex, Andrew. Anybody else? All right. I will forward you your information on to folks. Do you have any questions for me about that whole presentation or anything else? I have some experience in those places, working in those places, so I'm your friend if you have questions. Okay. Moving on. Let's get right into this. Chapter 19 homework. It's so late in the morning already. We'll just go through it quickly. Just let me know if you have. Let me stop and explain anything. So this is chapter 19, question 1. True or false? An inductance can have. What does X sub L mean? Since we've been on for a week, we might as well dumb it down. What does X sub L? Inductive reactance, and that the unit for that, either reactance, any kind of reactance in an AC circuit, what is the unit of measure? You measure reactance. Well, no, inductance is Henry's, but reactance, so capacitive reactance or inductive reactance, it's ohms. That's the most important part about all this. The reactance is resistance to current flow. Okay. So inductance can have a reactance to or a resistance to current flow to reduce the amount of alternating current, because self-induced voltage is produced to oppose the applied voltage. That's right, it's true. Good job, class. That's true. Good job. Frequency is equal to which one? 1 over T. And that's the same old formula. T is 1 over frequency. So frequency is 1 over T per period. How much reactance for a coil with negligible resistance that has 62.8 volts across it with 0.1 amps of current? Coil. And it's asking for X sub L. The voltage drop across it is 62.8. Current through it is 0.1 amps. So we got ohms, volts, and amps. So what formula? Just Ohm's law. So R equals E over I, X sub L equals E sub L over I sub L. 62.8 divided by 0.1. What do you get? And 28 ohms. Inductance equals. First, let's just write the inductive reactance formula. Remember, capacitive reactance was 1 over 2 pi FC, right? Reactance, or inductive reactance, is just 2 pi FL. So if we were looking for inductance, solving for L, we would divide this whole thing by 2 pi F. And this whole thing by 2 pi F. So L equals X sub L divided by 2 pi F. Inductive reactance is measured in which one? Ohms. Inductive reactance will increase if frequency is lower. You remember when we were doing this before? With capacitive reactance, and they were inversely proportional. And now we have now they're directly proportional. So we'll induct, in other words, if this goes up, this goes up, or this goes up, or both. So if any one of them go up, none of them can go down. They would all, or at least one of the other ones would go up. So inductive reactance will increase if frequency is lower. Nope. Inductance is increased. Yep. Inductance is decreased. Nope. Direct current is used. Nope. What about that last one? Do you get any inductive reactance with direct current? Nope. So the answer is inductance is increased, right? Right. Since reactance is an opposition in ohms, the values inductive reactance in a series of parallel circuit are combined in the same way as ohms of resistance. right, it's true. Good job. The base unit for inductance is Gilbert. Yeah, the Henry. The combined parallel inductive Gilbert's branch will be inductive reactance is a unit of ohms, right? If you have parallel resistances, does the resistance go up or down? Down. Combined parallel inductive reactance. Combined parallel inductive reactance branch. Will be less than the lowest branch resistance. Right? The same thing with resistors. They're in series, you'd add them. They're parallel, they go down because you're creating more more current path, right? Same thing with parallel inductive reactances. Combined reactance of parallel reactances is calculated by what? Yep. The higher frequency of the alternating current and the greater inductance, the inductive reactance opposition will be increased. So that's saying the same thing as this formula up here. Higher frequency, greater the inductance, the higher the resistance to current flow in the circuit. So the higher the inductive reactance. True. Inductive reactance is the ohms of opposition that an inductance has for sine wave current. Yep. The ratio of inductive voltage divided by inductive current specifies the inductive reactance. And that's really just spelling out Ohm's law, R equals E over I. The values of X sub L in series or parallel are combined. The resistive value, ohms, it's an ohmic value, so the same way as ohms of resistance. Is there inductive reactance for steady direct current? Nope. Very often, inductive reactance can be determined from voltage and current measurements. Yep. When alternating current flows in an inductance, the current is less than the DC resistance alone would allow. Well, yeah. You get what it's saying though? Why are you feeling like you're confused? Oh, really? That's cool. wire. Here's a wire. And if I put my meter on each end of this thing, it's going to give me some kind of resistive value, right? That's very, very, very low. Very small ohms. If I hooked up, whatever, 10 volts to this thing, it would probably burn up because there's really nothing resisting current flow there, right? If I coil this thing up, and this is kind of an exaggeration because it's just an example. Because of this turn, because of the turns in this, I've made it an inductor. Okay, this is a coil. And if I hook up DC to this, direct current, in other words, current's only going to flow from there to there in a steady, constant state. Same thing's going to happen. It's going to burn up. But if I put AC on there, it goes back and forth. I've created this expanding and contracting magnetic field, and that inductor is now resisting current flow a little bit. So this thing's not going to burn up. Does that make sense? So because of that resistive value, the resistance of that phenomena, the resistance of that inductor, the opposition to current flow, is called inductive reactance. And that's what we're talking about here. So if there's an inductive reactance in an AC circuit with this, then the current is going to be less than the DC resistance alone will allow. If I put DC on there, all I'm doing is it's voltage divided by I equals E over R, voltage divided by resistance. It's going to be enormous because there's nothing resisting current flow. If I put the same amount of AC voltage on there, we're going to get a much smaller current because it's resisting current flow. Okay? Clear things up a little bit? No? Not even paying attention? Good. Let's move on. Which of the following is not an example of how X-Val is generally used? Block DC. That's the capacitor's job. All right. With an inductive circuit, the phase angle between VL and IL is which one? 90 degrees. X-Val equals 2 pi FL. We already went over that. And that's it. Measure that indicates the relationship between the real power and apparent power. Real and apparent power value is. That's called power factor. We talked a little bit about that before break. This one's a dumb question. The answer is choke. You never need to use that the rest of your life. For a series RL circuit, when R is much larger than X-Val, yeah. Series RL circuit. Series R and L. A resistor and an inductor. When the resistance is much larger than the capacitive reactance, so let's make this X-Val. This is the reactance of this in the circuit is 1 ohm, and the resistance is 1,000 ohms. Is this inductor really doing much of anything? It's resisting current flow, but just a tiny little bit, not very much. It's negligible. So for series RL circuit, when R is much larger than X-Val, the total resistance, called impedance, is approximately equal to what? just to, yeah, because the inductor ain't doing shit, right? If we raise the frequency though of this circuit, this value is going to go up, right? According to our little doodad up here. Then that inductor is going to have more of an effect on that circuit. How much impedance for a 100 ohm resistor in series with a 100 ohm inductor? $141. How did you get that?
Was the square root of resistor squared times the reactance squared, or plus the vector reactance squared.
Okay. Yeah, I'm just catching up. Sorry. So 100 ohm and 100 ohm series RL. Is that on your formula sheet too? Look real quick and see if it is. So total impedance is the square root of R squared plus X of L squared. It should be on the page of your formula sheet that's RL series. And the answer to that is 141. In the series circuit, the higher the value of inductive reactance compared with R, the more inductive the circuit. Really dumb question. True. I don't even know how to explain that one. It's just like common sense, but also really stupid. But all it's saying is that, okay, if we look at the same circuit and this, the inductive reactance is bigger than R, we would call it a more inductive circuit. That's just dumb. I don't know why I didn't take that question out. In phasor triangles for volts and ohms in a series circuit, the phasor for R, IR, or VR is used as reference at 0. That's true, and that's the same as it was in capacitive circuits. Inductance has the useful characteristic of providing more ohms of reactance at, we're going to get more ohms of reactance at higher frequencies, lower frequencies, resonant frequencies, or harmonic frequencies. X sub L goes up, frequency must have gone up, higher frequencies. Power that is assumed to be consumed by the circuit is which one? Apparent. Real power is calculated by using the expression. Yeah, and that's on your ugliest book. The ideal condition of most power circuits is a power factor of what? That's ideal. Is it possible? Nope. We'll try to get as close as we can. The process of adding a capacitor across the AC line to offset the effects of inductive loads. Power factor correction. Now you can kind of see where we start using some of this theory to our advantage. Quality Q of a capacitor in terms of minimum loss is indicated by its power factor. The resultant of the phasor addition of R and X sub L is impedance. The unit of reactive power, VAR. What is the phase angle for the voltage of inductive reactance with respect to current through L? So inductive voltage leads inductive current by 90 degrees. And you can come to that conclusion by looking at your formula sheet. What is the phase relationship between IR and VA in a parallel RL circuit? IR, VA, parallel RL circuit. Yes, they're in phase. When sine wave variations of current produce an induced voltage, the current does what? Lags its induced voltage by 90 degrees. Yes. Which type of power is involved in any reactive circuit? All of them. Everybody happy? All right, I'll do a couple examples of things that we're not going to be quizzing over these chapters because we just don't have time, but things that you might see on the final. In solving these circuits, they're a lot like the circuits that we had with capacitive reactance. The only difference is the behavior of the reactances themselves are opposite in relation to frequency or proportional versus inversely proportional. All right, the first one, I'm just going to put 3 inductors in series. What is going on? And let's call this 150 ohms of reactance. Call it XL1, XL2, XL3. Call this 200 ohms. Call this 175 ohms. Okay. In this circuit, what would the total capacitive reactance be? Yeah. 3 ohmic values in series are going to resist current flow additively. They work additively. The total of these is in series, we just add them up. So it'd be 350, 4, 50, 5, 25. Is that what you said? let's call this 30 volts. So what about total current in this circuit? How would we find it? Is this also equal to total impedance in the circuit? Yeah. Because there's no resistors there either, but so all it is 30 divided by 525. And what was that answer? 57.1 milliamps. Cool. Does that mean that the current flowing through each of these resistors is 57.1 milliamps? Yes, because they're in series. So then we could find voltage across XL1, XL2, and XL3, right? So why don't you figure out what those are and tell me. EL1, EL2, EL3. Or what'd you get for the voltage across L1? Yeah, and all we're doing is multiplying them, right? It's just Ohm's law equals I times R. So 57.1 times 150, and what did you get? 8.57 volts. EL2, 11.43 volts. EL3, 9.999 volts. If you add all three of those up, what do you get? About 30 volts, right? Pretty straightforward, not too bad, right? You are, however, going to have the same type of solve this circuit with a resistor and an inductor the same way you had to before with a resistor and a capacitor. Now remember, it's kind of a lengthy process, but I definitely want to go through it together. What's your favorite restaurant? What?
Golden Corral.
Golden Corral. Mom? Uh-huh. I don't know. I don't remember. I don't remember. I feel like I bought some a while back. I don't know if they're in one of those bins. There used to be someone up behind the podium in 217, like on the desk behind the seat, you know. But I told them I would get them some. I just don't know. Okay, those ones should be new, right? Okay. No. No, I tend to throw shit away. Yeah. Okay. All right, see you. Okay. All right. Let's do series RL. Series R, series L. Let's call this 50 volts. AC. 10 kilohertz. And let's say this is 3,000 ohms. And let's say this is 200 millihenries. And we need to find all of the stuff. E total, I total, Z total. U R, I of R. R. E of L. I of L. And what would we call the resistance value of the inductor in the circuit? XL. So what can we put in there right away? We don't know XL yet, but we know R is 3,000 ohms. And we know E total is 50 volts. So given the information we have, there's really only one thing we can do first. Right, we find XL. So what is that formula? Two times pi times 10,000 times 0.2. What does that give you?
No.
4.56 K.
Yeah.
That sounds better. 12,560 what? 60? Okay. Ohm. That resistance value, or reactance value, resistance value of that inductor in the circuit is way bigger than the resistor's doing, right? So would you expect the voltage drop across this to be bigger or smaller than that? So this reactance is 12.5 K ohms, and this reactance is, or not reactance, but resistance to current flow is 3,000. which means that this guy here is gonna eat up about 4 times more of the voltage than the resistor. Something to just be thinking about for when we solve this later on. Okay, so can we find impedance? And what is the formula for that? Is that found on your formula sheet? Show enough. And what do we get for total impedance then? What is it?
12.92.
12.92 kilo. So call it 12,920. Okie dokie. Now what can we find? Which one? All of them, but we using the totals. We have 2 variables, so we can find the third. So E total is 50 volts, Z total is 12,920. So how do we find I total? E total over Z total. That can be found on your formula sheet. 50 divided by 12,920. And what do we get? 3 point what? 3.8 something? 7 million. The reason I'm asking is because on a final, it's going to ask you for 2 decimals. So 3.87 milliamps. It's okay. If we fall outside the tolerance that it marks you wrong, just let me know. I'll be going through all of them anyway to make sure all the answers are right. So all of these now, because we're in a series circuit, are the same, right? 3.87 milliamps. 3.87 milliamps. So we can use Ohm's law to figure out the voltage drop across the resistor and the voltage drop across the inductor. And what do you get for ER and EL?
11.6 volts for ER. 6 volts for
Remember what we were talking about before, where the reactance of the inductor is way bigger than the resistance of that. So the voltage drop is going to be way bigger than the resistor because it's eating up more of that voltage. So ER is 11.6 volts. EL is 48.6 volts. How do we feel? Comfortable with that or no? Want me to send you home with some practice? It depends on how far we get on Thursday. I'll send you home with a series example just like this and a parallel example to do on your own. We'll go over the answers on Thursday before we review for the final. And, right, it's the same thing we did before where we solved for capacitive reactants, right? All those same laws apply. Series versus parallel is solved a little differently though, right? And I think parallel is easier because voltage drop is the same across each rung. But, yeah, okay, I shall. Converting Henry's to ohms. The reactance, you mean? Yeah, no matter where that inductor is in the circuit, series or parallel, the reactance is dependent on frequency and inductance, right? So X of L equals 2 pi FL. That same formula applies to series or parallel. It's all dependent on frequency and inductance. Doesn't matter if it's series or parallel. So let's call this 40 volts, 8,000 hertz. Seven. Like 700 ohms and 40 millihenries. Yeah, I'm just making one. You can write it or I'll print one out. And this whole lecture that I've done, I'm recording it and I'm gonna post a link on Blackboard for you to look over. There's a few people that couldn't make it today because they're sick, so you should get an email when that video is available. This 9,000 hertz. That's fine. One series and one parallel. Okay. We're gonna do a really good review on Thursday, and then I'll also do some stuff. Once we have. I can.